if I have problems with the internet connection, which I do sometimes, the Zoom recording will show that too. And so the Zoom recording will be bad, but my recording will not be bad. And in fact, what I do with my recordings, I upload them to this YouTube channel so you can see them later. Okay, so you actually have two places you can see my lectures. You can either see them on Zoom or on this channel. If you want to subscribe to the channel, go for it. I mean, it's up to you. But my all my video lectures will either be on Zoom or on this channel called DC Physics, Rockland, California. Okay, can you all see that writing? I had to switch cameras this morning. My original camera died, so luckily I had a spare, so I'm working with a different camera. Okay. So this is Physics 210. I think what I want to do today is start with any questions that you may have that you saw because of the introductory video. Do you have any questions from the introductory video?
Yeah, you said the grading structure had changed. Does that mean you've gotten rid of the curve as well?
So yeah, my curve looks like this. I'll show you what my curve looks like. Because the exams are in class, it's more of a typical grading curve. And that's approximate. Okay, that's an approximate curve. So giving the exams in person allows me to give you guys more standardized problems as opposed to what I was doing the previous 2 semesters. The exams were online, and so I had to give non-standard questions. And I decided to curve just in case the exam grades were bad. In some exams, the grades were bad, like 40%. That's not going to happen with the in-person exams. Because the in-person exams, pretty much the exam average is between 60 and 80%. So it varies depending on the unit. And so this is what I've been using for years. And by the way, when I curved last semester, I mean, I ended up getting pretty much the same grade distribution as I usually do anyway. So does that answer your question?
Yes, it did. Thank you.
Okay. Other questions regarding the introductory video?
I have a question about syllabus. So it's about assignments and exams.
Okay.
So I'm using OneNote to take notes and for other things. And I was wondering, do you need us to have everything written down on paper, or could it be done digitally?
For your exams?
For notes.
Oh, for your notes?
Yeah, notes and for exams and assignments.
Well, your exams are in person, so they're going to be done.
Yeah.
Okay. The notes, I mean, they're your notes, so they're for yourself.
And assignments, there is something about
assignments. So the Webassign, you had 205 here last semester, right? Or not?
Yeah.
Okay, so we're going to be using Webassign to do the assignments. So they're all going to be done. I'm sorry.
Okay. Sorry. It's okay. I got it. Okay, thank you.
Okay, and I refer to worksheets in the syllabus.
Yeah.
And last 2 semesters, I had the students turn in the worksheets digitally. And it takes me a long time to grade things digitally. I'm just slower. Mm-hmm. And so I actually programmed them into Webassign. So the worksheets now are in Webassign. Okay, so in the lecture part of the course, the only thing that you're going to be handwriting are the exams. Okay, and turning in a hard copy. In the I'm sorry.
Okay, thank you so much for answering.
And I just want to mention in the lab, because I had an email, and I apologize, I never answered it because I was having problems with my computer this morning. In the lab, all your lab reports will be typed like you did in 205L. Any worksheets that I give you in the lab, you will probably turn in digitally. Okay, we're going to talk about the labs on Friday because it's a hybrid lab. Some of the labs you're going to actually make videos of your lab report, and some of the labs, in fact, most of the labs you're going to turn in a hard copy. And again, it allows me to grade faster. Okay, so we'll get to that on Friday. All right, other questions?
How do we access Webassign?
How do you access it? So
Yeah.
it's going to be different from what you did last semester. You actually just click on the assignment in Canvas and it'll take you to Webassign.
Okay.
I integrated it into Webassign, and there's a short description of it in the syllabus, and there's a couple of videos showing how to do it on Canvas. All you do is got to click on Webassign. You should be in the system, and if not, if it asks you for a username and password, use your MySierra username and your MySierra password. Okay?
Okay.
And then once you're in, you can just start working on the assignment. So that's the only thing that's different. And so the grade will be automatically recorded on Canvas. Okay.
While we're on the subject of homework, I was looking at the discussion boards and someone commented that the first assignment is locked until September 1st. Is that the case? Has it been fixed? Just letting you know.
That's a mistake on my part, and
Okay.
I need to fix that. Sorry. So the first assignment it said was locked? Okay.
According to someone's post, yeah.
Okay.
Yeah, I just tried it again, and it's locked until September 1st.
I'll fix that. Okay. Sorry about that. Okay. I'll fix that after class. Other questions? Concerns? Okay. So just go ahead.
So you sent us some PowerPoints through the email, right?
Yes.
Some of the text in that, I wasn't able to read it, but I'm not sure if it's like, if I'm opening it in the wrong program or something.
They should be PDFs, and you should be able to open them with Acrobat.
Yeah, because it's like some of the text seems small, so I wasn't sure if it just normally looks like that or.
Some of the text will be small. I mean, I'm hoping that I designed those notes for the when you're in person, and you print them out and you use them to take notes.
Okay.
And so they're basically the PowerPoint notes you see on the screen, except that they're made smaller. Otherwise, if you print them one at a time, one page at a time, it's a lot of pages.
Yeah.
And this makes the files smaller by doing it this way. But if you have trouble seeing them, I mean, I can make a version that's a full page per each one, but then you can't write notes on them.
Okay.
Okay, just let me know.
All right. Thanks.
Okay. Other questions? So anyways, as we discussed before, what you see on the screen is my grading scheme that I'm going to be using this semester, assuming all my exams are in person. And if I, for some reason, exams have to be done online for some whatever reason, closure because of fires or whatever, this might have to be modified some. Okay, just because if I give an online exam, and by the way, the online exams are usually a little bit longer too. The in-class exams are an hour and 20 minutes. Okay, like you would normally get. All right, so this would be my grading scale. These are the chapters we're going to cover this semester. I'm actually going to be doing something different. I'm going to actually start on relativity first. And then I'm going to proceed in a normal fashion. The reason why I want to do relativity first, because usually this is covered at the end of the semester. And people blow, I'll usually blow through it and I won't cover it in as much depth as that, I'd like. And it's an interesting topic. And really, because we're online, I have a little bit more time to cover this chapter. Okay, even though when we're online, we actually proceed a little bit slower. Okay. Notice one thing. We're going to have 5 exams this semester. And this is important that you understand it. I forgot to fix the paragraph at the bottom of the slide. You have 5 exams. The first exam is only worth 9% of your grade because it only covers 1 chapter. Okay? The other 4 are worth 18% of your grade. I will drop the lowest of your first 4 exams. I will not drop the last exam. I'm not giving a final. Okay? No final. I don't want to give a final in this with this weird online format. Okay? So there's no final, and not giving the final gives you more class time anyway. So we'll have 5 exams. The first one's only worth 9%. It's going to be on September 10th. Okay, and it's only in chapter 39. So the first chapter will be on relativity. It's weird stuff. It's unusual. You'll feel uncomfortable with it. But once you get to the end of the unit, you'll feel a bit more comfortable with it. At the beginning, it's going to be very strange. Okay, and uncomfortable. All right. If you have any questions on the lecture, your PowerPoint notes, homework problems, and conceptual questions. By the way, if you look on Canvas, I actually, in the modules, at the end of a couple of the units, I think it's units 2, 3, and 4, I actually have conceptual questions for you to practice on. If you have any questions on anything, on course material, I prefer that you ask it on the discussion board because somebody else in the class might either have the answer to it or they might have the same question. Okay, that way I can answer as many questions as I can, really. It's more efficient that way. Okay, because if I'm getting emails individually on the same question, it's not very efficient. Okay, so I'm hoping that you can use the discussion board. All right. Just some reminders. Make sure you read and understand the syllabus, not only for the lab, but not only for the lecture, but for the lab. It's due on Friday. The last page of the syllabus, if you turn it in, you get 0.5% extra credit. Okay, and I don't credit you till the end of the semester. I haven't figured out how to put that into the Canvas thing. I just look at, if you've turned it in, just look at your course average and then add 0.5% to it, okay? I fully expect you to read the book. All right, it's important actually you read the book, especially at this level. It doesn't have to be a thorough reading, just scan through it, just know what's in the book at least, okay? And I say there, get started on your first homework. Probably after Wednesday might be a good idea to get started on the homework. Okay, because a lot of stuff I'm going to say today is introductory material. Now, one of the things I have found somewhat successful the last couple semesters that we've been online is Discord. And one of you has been very kind enough to set up a Discord for the class. And so if you go on Canvas, I have the link to the Discord. And usually during the semester, I have it on my computer I have my computer on all the time. So if I'm by the computer and I see a question on Discord, I'll answer it. But it's a way for you guys to answer each other's questions. So if you don't want to use the discussion board, you can just use Discord. Okay, you can use it for labs, for anything. All right, so I encourage you to use them. I'm hoping that you guys get to help each other out as much as you can. In this format, you know, it's kind of a weird format, the online format, especially for a physics class. We need to help each other out, to help us learn the material. And I missed some chat questions. Question was, and I'm sorry I missed the question. Does the book come with buying Webassign? Yes, or you know, with Webassign, if you log in, if you actually sign into Webassign, you get an electronic version of the book. And I forget the price. Is it $100? You guys paid for it, so is the Webassign around $100? It's 119? Okay. So the unlimited is 119 and it's for 4 months. Isn't there a version? Isn't there one where you pay you can have it for the lifetime of the edition?
Yeah, there's one of those too. I bought it last semester. Okay.
I forget what the price of that is. We're trying to save costs on the book. If you buy the book by itself, it's like $250 or $300. Very expensive. Okay. So I'm hoping you get away using the electronic version of the book if you want. We have it on campus. I think it's a loose leaf version. Okay. And we're stuck at the 9th edition. They're at least the 10th edition. The publisher is allowing us to use the 9th edition for a while. So. Okay. Make sure you go to Webassign as soon as you can. Log into Webassign. Lab kits. We're going to be handing out lab kits this week. Actually, Monday, Tuesday, and Wednesday, between 8 and 4. Okay, so you just got to go to Sewell Hall, and somebody will greet you as you walk in. You actually, basically, you're going to be by the polar bears I don't know if any of you have not been in Sewell Hall yet because of COVID. But as you walk into Sewell Hall, you will see the polar bears. There'll be somebody there, and they will guide you.
Never seen it.
And they will give you the lab kit. I'm going to go to campus after this class. I'm going to be there for maybe an hour or two. So maybe if I see you, I'll greet you. Okay.
Then your dream would come true.
You got an open mic, Avi.
Okay. So if you cannot pick up a lab kit either Monday, Tuesday, or Wednesday today, I need to know. Okay. If you don't pick up a lab kit, that tells me you're not interested in being in the course. I need you to pick up the lab kit. So if I notice that you haven't picked up a lab kit, I have the ability to drop you. So make sure you pick up a lab kit. Okay. Now, for this unit on relativity, I started looking at this book called Basic Relativity. Hold on a second. Kind of looks like this. There's a version of it on Google Books, the author's mold, and there's really one chapter that's actually very useful for you guys. The rest of it is not. Okay. The chapter 2, if you go on Google Books and you want to look at this book, has a nice description of some of the material, the basic ideas of chapter 39. And that's really all you need to look at. Okay. So you might be interested in just going to Google Books and look at that. So what I want to do today is talk about the ideas that started relativity, where did relativity come from. I'm going to skip a lot of important details in discussing relativity. There was a lot of interesting experiments that took place, a lot of discussions that took place regarding this idea. I just don't have time to go through everything, so I'm kind of summarizing everything. Not even your book goes through all the details, okay? There's just a lot of information. So I'm going to summarize really what were the issues that led to the development of relativity. And I'm going to talk about Einstein's postulates, and I'll probably stop at time dilation and Lorenz contraction, okay? These two items are very interesting, and then it gets even weirder as we go on past this. On Wednesday, I'll do the even weirder stuff. Any questions before I proceed? Okay. So, our first exam is going to be on September 10th. We're going to meet in room S102. A couple of things you have to understand that when we meet in class. Number one, when you enter the building, before you enter the building, you have to be cleared to enter the building. And so on your smartphone, if you don't have a smartphone, we have a handout that you can fill out. On your smartphone, you're going to have to, you have the Sierra College app. The Sierra College app, there's a screening on there. You answer the questions in the screening, and if you pass, you'll get a red star, and you can enter the building. Every room you enter, when you're in Sewell, you have to use your Sierra College pass and scan the QR code. Okay? Good question, Aaron, regarding the exams. I have on the exams the equations you'll be needing for the exam, but I won't allow any flashcards or little crib sheets for you. Okay, it's all based, I'll give you my own equations, okay? The main ones, okay? So when you walk in, you need to make sure that you're actually past our scanning system, or pre-screening. And then when you sit down to take the exam, you're going to have to wear the mask so that it covers your, so the mask covers your nose and under your chin. Okay? So that's going to be important, and probably going to keep reminding you of that throughout the semester. Okay? Questions on that? And I think you've received email, you've seen emails of videos and stuff like that regarding this issue.
So when you take the screening, is the pass good for like 24 hours and then it like times out?
Yes, it's for 24 hours.
Okay.
Yeah.
Thank you.
And for each room that you go into, you have to actually scan. There's a little QR code in the room, and you just got to scan it. And it's only once. You just need to do it once. Okay. As long as if you're vaccinated and you have if you have a mask on, and you always keep your hands clean, you should be you're pretty well protected. We will have sanitizers in the room, so you can keep always sanitize your hands, okay, and sanitize your desk too that you're at. All right. Okay. I forgot one more thing. We do have tutors. I have the tutoring schedule online. Some of the tutors are in this class. Okay. So we're having a hard time getting tutors. So for this first unit, it might be a little bit of a challenge with tutors. Because the way I've been covering the last two semesters, not all tutors have seen what I've done, okay? I think there's one tutor who had 210 last semester with me, and he can probably answer your questions. His name is Andrew. All right. Ideally, we'd like to have tutors available throughout the day, but within this format, it's very difficult to get tutors. So if you go on Canvas, check the tutoring schedule. Okay, the tutoring room on Zoom is open from 12 to 4:30. Okay. Oh yeah, and one more thing, and I keep forgetting things. I'm going to try to be on campus on Mondays. So after I teach this class, I'm going to head to campus, and if you have if you have questions, you can always come see me on campus. Okay. Some of your labs, your first few labs are going to be done at home with the lab kits we've given you. And so if you have questions on how to do the labs, your lab kits are small. You can bring your lab kit with you and you can show me what you're trying to do and I can help you with it. Okay? And then on Fridays when we have the exams, 1.5 hours before the exam or 1.5 hours after an exam, I have open lab. And my open lab schedule is on Canvas. And so I have to be there to answer your questions. So I do have quite a bit of availability. So when we have those exams or we have the labs, I'm going to be there not only for the lab meetings or for the exams, but I'm going to be also available to answer questions on the laboratory experiments. That's going to make it easier because it's a pain to answer questions on labs online because you can't see anything. Okay. All right, let me switch PowerPoint notes. Okay. So let's start talking about chapter 39. Unless you have another question, I'm going to start with chapter 39. And we're going to discuss relativity. I want to talk about the origins of why this idea, where this idea came from. Our book has a short chapter on this topic. I mean, there are schools that teach an entire course on this topic. I mean, this book that I showed you is essentially for an entire course. Okay, maybe not the whole book, but there's a lot of information in relativity, but we're just going to give you a summary of it. You're probably never going to see a discussion of this again unless you're a physics major, okay? And most of you folks are not physics majors. So I want to talk about the origin of thought, where these ideas came from. So I'm going to do a little bit of review of a topic that you probably barely covered in Physics 205. And then I'll talk about some implications of it. I want to talk about something you learned in 205 called the Galilean Transformation. Do you remember this? Don't remember it? Okay, so I'm going to remind you of the Galilean Transformation. It's fundamental to this idea of relativity. And by the way, the relativity came from the fact that from a problem that existed with the laws of electricity and magnetism. Okay, so when Einstein came up with his famous papers, it had to do with him analyzing the laws of electricity and magnetism. And really combining it with this thing called a Galilean transformation. So let's say we are in a school bus that's moving. And let's make the math easier. Let's just assume that the school bus is moving to the right. So here's a school bus. I'm not an artist, okay? So I'm going to draw a very simple school bus. Okay, that's my school bus. Going with velocity v. And I'm going to attach to it a coordinate system. I'm going to call this y prime, and I'm going to call this x prime. And the bus is moving to the right. And we are in the school bus. Okay? And let's say one of us throws a ball to the right. Okay, so one of us throws the ball to the right with some speed u prime. And at this moment in time, its location is x prime from the origin. Or from where I threw it. Or where one of us threw it. Okay. Does that make sense so far? Okay. Now, let's suppose we have some observer outside the bus that's fixed. The fixed observer sees this ball that one of us has thrown to the right. Now, the fixed observer says the location from him or her is x. At some time t, okay? At some time t, and by the way, this coordinate system I'm going to call y, and the x-axis I'm just going to call x. So the moving one, I'm going to always say it's the prime system. The stationary one, the one that's moving relative to us, is the prime system. And the one that's stationary relative to us is the unprime system. Okay? So after some time t, the bus is a distance v times t from us, from observer. So that means that this distance is v times t. And this distance is x prime. Is there a way for me to write the location x prime in terms of what the fixed observer sees? Of course. Isn't this going to be this distance minus that distance? Isn't x prime and x do those make sense to you? Right? Those make sense. Those should make sense for you. Well, that's the Galilean transformation. That's how you transform measurements between one coordinate and the other. Okay, let me lower. Hold on a second. The audio is a little bit bad. That's not
It's
good.
a little harder to hear as you move away from the mic.
The mic is right. The mic is right here. So.
Oh.
Hold on a second. Let me make sure I am using the right mic. It wasn't using the right mic.
Okay.
I don't know why. Can you hear me now?
There. Yeah, that's better.
Okay. I don't know why. Usually it automatically switches. Sorry about that. Thank you for pointing that out. Okay. Yeah, you're right. It was using the mic on the computer. Sorry. Okay. Yeah, by the way, if anything is hard to see, hear, just let me know right away. Okay, so after some time, the bus is a distance v times t from the observer. And we can easily deduce these equations. Isn't that true? This describes this position, the position of this object at that instant in time in terms of what this person measures. And this position represents this coordinate in terms of what we measure. That's the Galilean transformation. Okay? Now, let's take a look at this transformation. Suppose I want to calculate the expression for the velocity of this thing. Well, I just got to take the derivative. And that's going to give me dx over dt minus v. So I'm going to call this is the speed of the object that this person measures. And so I'm going to call it u. Furthermore, if I take the derivative of this one, I get u equals u prime plus v. Does that make sense? Look okay? Okay. So what does this mean? Okay. Let's suppose the bus is moving at 30 miles per hour. So let's let v be 30 miles per hour. And one of you who threw the ball threw it at 20 miles per hour in the forward direction. If this person measures the speed of the ball, what are they going to measure?
It's not a trick, right? It's just going to be 50.
It's 50. Yeah, that's it. Okay. I mean, it's a common experience to us, right? I mean, that's how we measure relative velocities. So there's a question in the chat about how did u prime turn into x minus t? Where is that? I'm not understanding the question.
I think I understand this question. How did x prime, when you differentiate, turn into du prime over dt? On the other side of the equal sign.
Oh.
Yeah. It's dx prime,
Yeah.
is it not?
Yeah, that's a mistake on my part. Sorry. I was thinking ahead.
Then the u primes and the u would be x prime and x on the other equations, right?
You mean here?
Yeah.
Well, u prime. What do you mean x prime?
Never mind. I think I know what I did. Okay.
So I know in calculus you write the derivative as something primed, right? Is that what you're saying? Okay.
Yeah,
Okay.
that's where I got confused. But isn't it just the velocity? That's why it changes, right?
Yeah. I use it as U to represent the velocity. The prime is to distinguish it from the unprimed.
Okay.
In
Thank you.
fact, in physics, this means time derivative. You'll learn, if you're a physics major and you take a junior level class, you'll see that the physicists will write it with a dot over it because we use a lot of primes. Okay, so this makes sense. So that's how we measure relative velocity. In fact, let's take this one step further, okay? And let's take the derivative of u and the derivative of u prime. Let's pretend the bus is moving at a constant speed. Okay. So I want to take du prime over dt. Well, that means I got to take the derivative of this with respect to time. And the derivative of this with respect to time. But I'm saying that this speed's constant, so this is 0. And so that tells me du prime over dt. So that means that the acceleration, if this ball were accelerating and this bus was moving at a constant speed, then no matter what frame you're in, the acceleration is the same. As long as the bus is moving at a constant speed. We say that the bus is an inertial reference frame. Okay? And that's important. Okay? Because if the bus were accelerating, then this term would not be 0 and the accelerations would be different. That would mean if I applied the same force, if I just applied a force to an object, 30 newtons, let's say, the acceleration in one frame is going to be different from the acceleration in another frame if the reference frame is accelerating. That means Newton's second law is not valid. Right? Newton's second law is valid in all inertial frames. Okay? The fact that the bus is moving at a constant speed says that these two are the same. So if a force is causing this acceleration, then that same force is going to cause the same acceleration in the other frame. Otherwise, Newton's second law is not valid. And we're going to focus here on inertial frames. We're not going to look at accelerating frames because that's general relativity. I don't want to deal with that. Okay? Now, so the net force on the system in an inertial frame has the same value in all inertial frames. When you look at F equals ma, whether I do this in one-dimensional or three-dimension, this quantity is the same in all inertial frames. Okay? This quantity never changes in all inertial frame. And so we say that this is invariant in all inertial frames. You won't see that term in the textbook, okay? I want to mention it to you because it's actually never really described very well in any textbook. But it just says that Newton's second law is invariant in all frames. Newton's second law not only has the same form in all frames, but it has the same value in all frames. And that's what makes it invariant. Not all the laws of physics have the same value, give you the same value in all frames. But all the laws of physics have the same form in any inertial frame you're in. This is called the principle of relativity. So let me give you an example, another example of this. Right? Newton's second law is not only covariant, it has the same form in all reference frame, but it's also invariant. It turns out all the laws of physics and mechanics are covariant. They have the same form. Let's consider conservation of momentum. What is conservation of momentum? You have two objects that collide. M1, V1 initial plus M2, V2 initial has to be equal to M1, V1 final plus M2, V2 final. You guys remember that? I hope. That's from Physics 205. Okay. No matter what reference frame you're in, this equation is the same. But if you change reference frame, what's going to change? These values. If you do this, if you write this equation in a different reference frame, these values will be different. But the total initial momentum equals the total final momentum. Same thing with conservation of energy. Kinetic energy, its value is different in different reference frames. But the fact that the total initial energy equals the total final energy is true regardless of what reference frame you're in. And so we say that conservation of energy, conservation momentum, they're covariant. They have the same form in any reference frame. Their values will be different, but so what? Okay. This is the principle of Newtonian relativity. Okay. This is the principle of Newtonian relativity. Okay. So we'll go from that. So an important idea is the fact that all the laws of reference frame, all the laws of mechanics have the same form in any inertial frame. Okay? We're only focusing on inertial frames, meaning the reference frame, like the bus, is moving at a constant speed. By the way, like I said before, these equations can be generalized to 3 dimensions, but that's not important for the purposes of our discussion, okay? All right, something's not working here, sorry. In fact, the principle of relativity says that all inertial systems are equivalent in describing a mechanical system. There's no such thing as absolute motion. There is no absolute reference frame. Okay? Now, is this idea applicable to electricity and magnetism, the subject that we're going to be covering this semester? Okay, that's going to be a big question. So if you measure the period of a pendulum in two different inertial frames, you get the same period. You get the same result. Okay? Well, how does, and I gotta introduce a term. The question that I have on the screen says, how does the Galilean transformation work with Maxwell's equations? Maxwell's equations are the four main equations you will learn in this course. Okay? Well, what we're going to do is build up to them. Okay? We're going to build up to something called Maxwell's equations by the end of the semester. They're the four equations that pretty much summarizes everything you learn in this course. And they're differential in nature. It doesn't matter what they look like to you right now. Okay? But the question is this. If we apply the Galilean transformation, this, to Maxwell's equation, what happens? It turns out they don't have the same form. They're not covariant. If you apply this to conservation momentum, you'll find that the equations have the same form. If you apply this to conservation of energy, you'll find that the equation have the same form. But if you apply this to the laws of E and M, you will find that they won't have the same form. So to Einstein, that was a problem. Okay? Why is it? I mean, this should be something universal. All right? It's based on measurements. Why is it that this doesn't work for E and M? Okay. I'm not going to show you an example because we haven't covered E and M yet, so. So this is what it implies. It implies one of three things. Either Newtonian relativity doesn't work for E and M E&M, electricity and magnetism, only work in a special reference frame, or it implies that the laws of electricity and magnetism, which are basically guided by Maxwell's equation, they're not correct, but this is valid. Or it implies the laws of E&M, the last thing is the laws of E&M are correct, and there's something wrong with this. Maybe it's only approximately correct. Maybe we have to figure out a correction to it. And the question is, which did Einstein look at? Okay. What did Einstein look at? Now, again, there's a lot of information that I'm glossing over, I'm just skipping. There's a lot of stuff here that you can talk about, but I just don't have time. At the time where we learned about electromagnetic waves, Maxwell's contemporaries believed that light required a medium like sound waves. So I don't know how many of you folks have taken 215, but if you take 215 and you talk about sound waves, you will learn in order for sound to travel through a medium, well, in order for sound to travel, it needs a medium. It needs one part of the medium to be able to affect the next part of the medium. And that the stiffer the medium is, the faster the wave travels through the medium. That's what you learn in Physics 215. You'll talk about the properties of sound waves. What does the speed depend on? Okay. Well, the speed of light is much higher than the speed of sound. So the speed of light, let me write it down. Speed of light is this value. Okay, speed of sound in air, approximately, okay? So it's 1,000,000 times faster. So that means if the speed depends on the stiffness of the medium, it means that this thing has to be really stiff. Now, light waves can travel in a vacuum. So what kind of medium is required to have light waves travel? Well, the medium has to be very light. If it can travel through a vacuum, then the medium probably doesn't have any mass to it. It's very strange. So this medium they called the ether. And so they postulated that the speed of light, we can measure the speed of light with respect to the ether. Okay. Technically, it's called a luminiferous ether, but I just call it the ether. Okay. And the ether is supposed to be very, very rigid because C is large. And the speed of light is measured with respect to the ether is C. So if it's moving through the ether, that means if we move relative to the, if we can, there's a way we can actually measure the speed relative to the ether. If we move relative to the ether, maybe we can measure a different value for the speed of light. So experiments, a famous experiment was developed by Michelson and Morley to show or to see that the speed of light, or to show that the speed of light depends on reference frame. They devised this device. It's an optical device, and unfortunately I don't have time to go through it, to measure the speed of light as a function of the reference frame. And no matter what they did, no matter what they tried with this device, I mean, it's an ingenious device, and it's simple. They got no result. No matter how they weren't able to measure a change in the speed of light, no matter how they did the experiment. They got no result. So it's an experiment that gave no result, but that was important. Okay. That means the speed of light does not depend on reference frame. That actually threw out the idea of the ether. Now, independently, or we're not sure, nobody's sure whether Einstein used this idea to come up with his postulates. Okay, there's debate as to whether the Michelson-Morley experiment affected Einstein's ideas regarding relativity. Okay. And I'm telling you right now, I'm skipping a lot of historical stuff, which is unfortunate, but Einstein came along and he was studying this problem too. And he came up with a couple postulates. Einstein's first postulate says that all the laws of physics are the same in all reference frames. Okay. Not only Newtonian mechanics, but also electricity and magnetism. He said, let's say all the laws of physics are the same in all reference frame. Absolute motion can't be detected. See, with the idea of the ether, there's an absolute reference frame. He said, let's assume there's no absolute reference frame. All the laws of physics are the same in all reference frames. He extended the principle of Newtonian relativity to electricity and magnetism. Okay. His second postulate he came up with The speed of light is independent of the motion of the source. What does that mean? Can anybody tell me what that means?
Regardless of whether or not you give light a initial velocity greater than 0, it's always going to travel at c.
Yeah, if you're on a train, this is the bizarre one, right? If you're on a train, and again, this is a postulate, right? It's not like, which means there's no proof behind it, but it works. If you're on the bus that's moving really fast, let's say half the speed of light, and you shine a beam of light at c, somebody over here is going to measure the speed of that light beam to be this value. Okay, it doesn't matter. That's what it says. Which is bizarre. Okay. And from that, from these two ideas, Einstein was able to develop his theory of special relativity. It turns out that you can develop a lot of the principles in the theory of special relativity without even invoking the second postulate. After he came up with his equations, there people actually derived some of his equations without invoking the second postulate. Okay. Again, these are things you can't really prove, right? I mean, you learn it in geometry. Geometry, the science. I mean, the geometry has postulates. I mean, there's a famous one in geometry. You have a line and a point. There's only one line you can draw through that point that's parallel to this line. It's called it's a postulate. I forget the exact name of the postulate. You can't prove it. You can't prove it at all. But it works. Okay. So that's the second postulate. And so that second postulate has a lot of important implications. And it actually means that time intervals are frame dependent. That means clocks run at different rates in different reference frames. That's what that second postulate implies. Okay. So, let's do a little thought experiment using Einstein's second postulate, and let's see what this means. By the way, I'm not going to really derive all the equations that come from these postulates. I'm going to talk about the implications. One can derive what are called the new set of transformation. That's one thing I didn't mention. You know, this equation changes as a result of those two postulates. Okay, as a result of those two postulates, the Galilean transformation changes. But you'll find, though, when you derive a new set of equations that allow you to transform from one reference frame to another, you'll find that if you're moving slow enough, it reduces down to this. So this works okay as long as you're moving slow, but if you're going really fast, close to the speed of light, this is not valid anymore. You can't use it. Okay? And so the transformations, the correct transformations, are called the Lorenz transformations. We'll talk about later. I'm gonna write them down. I'm not gonna derive them because it's not of interest for us, at least to derive them, at least here. Okay. So what we end up getting is the Lorenz transformations. Okay. These are correct. I won't show you the equations yet. But if you move slow enough, in the limiting case when where the speed of the object is way less than the speed of light, then it still works okay. It's still a good approximation. Okay. The reason why Newtonian physics works fine is because most of this works fine is because all the objects we're talking about are moving at slow speeds relative to the speed of light. But if the objects move very close to the speed of light, this has to change. Newton's law has to be rewritten in another way because Newton's law is an approximation. This is an approximation to something that's correct. Okay? Everything we're learning, you learn in 205 is approximately correct. Okay. So let's do a thought experiment based on Einstein's second postulate. And let me check the time. Okay, I can do this in 11 minutes. Suppose we have a person in a rocket. Okay? So let me draw my rocket. I'm going to use black color. And there's a mirror. And this person sends a beam of light to the mirror and back. Okay? And the distance to the mirror is d. So this distance is d. So the total time it takes for the beam to go to the mirror and back, and this we're going to, since the rocket's moving relative to us, the total time, delta t prime, is twice the distance over c. Everybody okay with that? So that rocket's moving to the right, according to us. We're stationary. We watch that rocket go by. That person measures this time interval. And that seems fine, right? I mean, there's nothing that doesn't make sense there, right? Now, what do we measure? What time interval do we measure? That's the question. Well, what does the rocket do according to us? Well, the rocket starts here. I got to draw that higher. That's fine. Yeah, let me draw a little bit higher. I need some more space. So here's the mirror. So here's the beam going. Actually, it's going to go like this. Then over here, this is what we see. Oops. Isn't that what we see? If that rocket goes by us, we see the beam do this. Because the mirror is here after some time. Okay? That's what we see. So what time interval do we measure? Okay. Well, first of all, this distance is d. This distance is v times delta t. Because delta t, actually this is v times delta t over 2, because if delta t is the time it takes for the light to go from here to here, then the time it takes for the light to go from here to the mirror is half that time. And then this distance.
Are you pointing at things? I don't think we can see you.
Yeah, I believe your camera froze.
Oh, my camera froze? Darn. Did freeze. Okay. All right, let's see. We're at the end, so I'm going to, let's try this. It's too small. Okay, let me restart the videos. Let me restart it, unfortunately. Is that better now?
Yep.
Okay, sorry. I don't know why today I'm having all kind of problems. It's the first day already, first day of the semester. So this is the slide we're at, right? The light beam, according to us, we're not moving. The rocket's going by us. The light beam hits the mirror and then comes back to the person. That rocket goes by us. That's what we see. If this distance is d, this is half the distance from here to here, then this distance d squared plus v delta t over 2 squared. So let's say the time interval that we measure for the beam to go from here to here is delta t. The time interval for the beam to go from here to here is c delta t over 2. And that distance is d squared plus v delta t over 2 squared. I square both sides. Okay, so let me put this on the other side. And so delta t squared so delta t, if I take the square root of both sides, let me factor out a c from here. Oops. Let me factor out a c. I'm going to call gamma 1 over the square root of 1 minus b squared over c squared. Okay, and I'm going to say that delta t is gamma delta t prime. What can you say about gamma? Is it bigger than 1 or less than 1?
Less than 1
It's
or greater than 1?
It's greater than 1, right? Because this is 1, because c is the limiting speed. So this thing is going to be less, so this thing is going to be less than 1. So gamma is greater than 1. So what does that say? It says that I measure a larger time. So we measure a larger time interval. The rate at which the clock ticks is slower for the person in the rocket. Moving clocks run slower. So this is something you have to give up now. You're so used to the clocks running the same in every reference frame. That's not true. This is not something that appears to be true. This is something that you would actually measure. Because everything in here is based on what you can measure. It's not an appearance, it's reality. Okay? So, if we see that rocket go by us, and we see the light beam take a minute to go from, from observer back to observer, the observer is going to experience a smaller time period. The observer will measure a smaller time period. It's not an appearance. This applies to everything like biological systems, radioactively decaying system, etc. Okay, this is a measurable thing. It's someone moving in a moving frame. Their clocks will run slower compared to us. And I'm going to try to be careful, and I make this mistake all the time. I don't want to say appear. I want to say you measure, okay? And even books will make that mistake. Things appear to look like this, but no, it's you measure it, because the word appear is confusing. Okay? So moving clocks run slower. The rate runs slower. Okay? An observer in a frame that's relative to two events measures the events at the same location in space. The observer in a frame that's moving actually needs two synchronized clocks at two locations to measure the time interval. The time between two events that happen at the same location is called a proper time. So the person in the rocket is measuring something called a proper time because the two events happen in the same place. We're not measuring the proper time because the two events happen at different places. Okay. I think I'm going to stop here. I'm going to continue my discussion on Wednesday. So it gets crazier on Wednesday. Do you guys have any questions? Concerns?
I guess I have a question about the reading. Should we read all of chapter 39 in its entirety, or leave some of it?
You don't have to read it all. You don't have to read it all at once. I mean, I would read up to like 39:4. Read all the way up to maybe the Lorenz Transformations.
Okay, thank you.
Okay. It's reading the whole text at once is hard because there's a lot of information to digest. Just
Oh,
read
yeah.
It, yeah, read
I
it
break
slowly.
it up. I just don't know if there'll be parts of the chapter that aren't relevant to us.
Eventually, you'll end up reading the whole chapter by the time we get to the exam time, but just read it slowly. And I wrote in the syllabus, I try to break it down per day in terms of what you want to read.
Okay, thank you.
Okay. Are there questions?
I was gonna ask, how did you get the root over d squared plus the v d delta t or 2 squared? Because I just got lost in that part.
Oh,
Can you
that's
explain
part?
how you got that?
So,
How you got that?
well, I use the Pythagorean Theorem.
Okay.
All right, this squared plus this squared is that squared. Because when you get to this middle, and there's gonna be a right
Right angle.
Other questions? All right, so hopefully maybe I'll see you today. Like I said, I'm going to be there for 1 or 2 hours on campus today. So I'm going to probably leave in a few minutes. So go ahead and pick up your lab kits. We'll see you on Wednesday or maybe today. All right? Email me if you have any questions. So long.
Thank you.
Thank you, Professor.
Thank you, Professor.
You're welcome.